Next topic is phasor impedances. At DC, we have V equals IR. The resistor is the impedance of the circuit. At AC, I have both inductors, capacitors, and resistors. Each of those is represented by a complex number. The complex number represents the relationship between current and voltages. Those are called the phasor impedances. The objective is to represent resistors, inductors, capacitors as a complex impedance and determine the impedance of an RLC circuit like this. Basically, it's just like we did at DC. I've got impedances in series add. In parallel, the add is the inverses, sum of the inverses inverted. Whatever we did at DC also works at AC, only now we're using complex numbers. Now to start, let's look at a resistor. From before, if you have a current or a voltage that's a sine wave, the generic form is A cosine omega t plus B sine omega t. In phasor form, it's A minus JB, where A, the real part, is a cosine minus J is sine. The relationship between voltage and current for a resistor is V equals IR. So in phasor form, it's the same thing. It's V equals IR, where I is a complex number. R is just R. So the complex impedance of a resistor is just R. Nothing really changes. If I look at the voltage-current relationship for a resistor, it looks like this. If I have the voltage going through a 833 ohm resistor, here's the current. Notice that the current is in phase with the voltage. When the voltage is large, the current is large. When the voltage is negative, the current is negative, and the zero crossings line up. So voltage and current are in phase for resistors. Now let's look at a capacitor. For a capacitor, I equals C dB dt. If the voltage is a sinusoid, in phasor form it'll be A minus JB. The current is C times the derivative voltage. The derivative of cosine is minus sine. Derivative of sine is cosine. Doing some algebra, in phasor form, the current is J omega C times A minus JB. You'll see the lecture notes for more detail on that. The impedance then is just voltage over current. The A minus JB cancels, and I'm left with 1 over J omega. So the impedance of a capacitor is 1 over J omega C. What that looks like in terms of voltage and current, if I have a voltage, the blue line, the current will be 1 over J omega C times the voltage. 1 over J is minus J, or minus 90 degrees. From V equals IR, the voltage is 90 degrees behind the current. Voltage lacks current, or current leads voltage for capacitors. For inductors, the current-voltage relationship is V is L di dt. If the current is a sine wave, sine and cosine, its phasor impedance will be A minus JB, again A is cosine, minus J is sine. Plugging it in, take the derivative of current, putting in phasor form, you wind up with the impedance of an inductor is J omega L. What that looks like is, suppose I had an inductor with an impedance of J 833 ohms. If the voltage is 1 volt, the current in milliamps will be the red line. The current is delayed from the voltage and changed by 1 volt over 833 ohms. Note that voltage leads current for inductors. To remember that relationship, there's a saying, Eli the Iceman. For inductors, L. Voltage leads current for inductors. For capacitors, C. That's ice. Current comes before voltage. So just remember Eli the Iceman. Voltage leads current for inductors. Current leads voltage for capacitors. With that, you can sit there and take a fixed value, 100 ohm, 100 millihenry, 100 microfarads. As the frequency changes, you can calculate what the impedance is. Got to remember that the natural frequency is 2 pi f, so whatever we say in hertz, you have to multiply by 2 pi to get the natural frequency. Resistors don't change. 100 ohms at DC is 100 ohms at 100 hertz, 100 ohms at 10 kilohertz. For inductors, the impedance is J omega L. As the frequency goes up, the impedance goes up. Plus there's the complex part, the J part. That tells you that Eli the Iceman, voltage is leading current. There's a phase shift. For capacitors, capacitors are 1 over j omega c. As frequency goes up, the impedance drops. And from ice, current leads voltage, that gives you minus j impedance. Okay, inductors are different than capacitors. Inductors have a plus j, capacitors have a minus j impedance. For RLC networks, with that, I can analyze the circuit like this and tell you what's the impedance between A and B. To do that, I need to start using complex numbers. Here I've got 2 resistors in parallel, 2 in series, 2 in parallel, in series. I need to do both parallel and series operations. So let's illustrate how you do that with an HP calculator. Here I've got 2 impedances in parallel, 200 ohms and minus J250. So let's take 200 ohms, 1 over R1 plus 1 over R2. Enter minus J250, 0, enter 250, negative, there's minus J250, 1 over R2, add the inverses. These two together give you 121 minus J97 ohms. Now this is in series with 40 plus J50, actually 50 plus J40. Take 50, enter 40, complex, there's 50 plus J40, add those together. I'm now at 171 minus J57 ohms. That's in parallel with minus 150 in parallel with 100. So take 1 over R1, put that in parallel with minus J150, 0, enter 150, negative, complex. Inverse, add that together. In parallel with 100, 100 inverse, that's 50 minus J27 ohms. Now add 30 plus J20. Voila, there's the answer. 80 minus J7 ohms. Second example. Here's a circuit. Find the resistance between A and B. Again, we're using complex numbers. These are in series, that's 40 minus J70. These are in series, 30 plus J50. These are in parallel, series, parallel. So again, using an HP calculator, let's clear the stack. I've got 40 minus J70. 40, enter 70, negative. There's 40 minus J70. That's in parallel with 30 plus J50. 30, enter 50. 30 plus J50. Take that inverse, add the inverses. These in parallel give you 62 plus J16 ohms. In series with 20 is now 82 plus J16 ohms. That's in parallel with 60 minus J70. In parallel, the inverses add, take the inverse. So take the inverse, 60, enter 70, 60 minus J70, take that inverse, add the inverses, invert. There's your answer. This is 48 minus J15 ohms. You should have a calculator that can do that. If you don't, get a calculator that can do computations like that. I highly recommend the HPs. The HP42 is nice because it's free. Normally you can't use those on midterms, but now the classes are remote. I suppose you can use them on midterms. The HP42 is the current version. It's a $50 calculator. Get a calculator that does complex numbers. You're going to need it. With that, we can now do complex impedances and complex voltages. Put those together, I can start doing circuit analysis, voltage nodes, current loops, and Thevenins. Those will be our next lectures.